Hello and welcome to the Directions Mag Geospatial webinar program, sponsored today by our friends at Hexagon Geospatial. Today we are excited to have Simone Cola with us from Hexagon Geospatial. He is joining us live from Italy. He's going to show us the latest with Imagine and how it can fit into your organization's workflows. Welcome, Simone. We are thrilled to have you with us today, and
Thank you.
excited to learn more about how to make this work.
Thank you. Thank you very much, and welcome to this webinar. And today we are here for understanding how Imagine can help you with artificial intelligence and for improving your remote sensing projects. So let's have a look now on the agenda for today. And we will have some remote sensing challenges and how artificial intelligence can help you on solving these challenges, and how we as Hexagon Geospatial, we can put artificial intelligence in action through our spatial modeler engine. And of course, we will have some, let me say, ideas on how artificial intelligence can be used in action using mainly deep learning operators and some case studies in order to give you a much more understanding on how to use this kind of technology as an operational world. So let's have a look now on the remote sensing challenges. So in just 5 years, there will be more than 1 million times geospatial data. This is a sentence coming from Robert Cardillo, director of NGA, and this means that yes, we will have 1 million times and 8 million analysts required in order to analyze all the remote sensing data. As you can imagine, it's quite impossible to have 8 million analysts and analyzing everyday imagery on the field. So this is why we are here for solving problems using artificial intelligence, even for the future, for now and for the future. So we do have many remote sensing challenges in different domains. If we look to imagery analysts, they have a very huge number of data to be analyzed, to the use of more and more sensors. We do have a huge amount of sensors at worldwide level that are delivering data and imagery every single day, possibly every hour. And their challenges is not to have better data, but getting better intelligence from this kind of data. And this needs to be fast and accurate. Land and the urban planners need to have an economical and extremely accurate and fast assessment of land and development. This is a key requirement because every day our landscape is changing and our cities are changing. So especially urban planners, they need to plan for the future, let me say, the development of the cities and of everything that is close to them, like infrastructure and any other kind of, let me say, urban relation. Agriculture agency and farmers needs to increase the agriculture productivity and sustainability, and of course, using remote sensing, you can extract a very sophisticated and complex information. But even in this case, this needs to be really fast and accurate. And at the end, the data producers capturing satellite, aerial, and now UAV images, they need to increase data processing for productivity reasons. Yes, because basically most of them, they are selling data, they are selling services, and they need to deliver information as a service most of the time to the end users. So how artificial intelligence can help in this kind of domains? So artificial intelligence can create efficiency, and using machine learning algorithms or deep learning algorithms for geospatial data sets. Of course, we need to discover pattern, shape, size, tone, and texture of images. So all the combination of these items are giving a better understanding of what we need to discover, and even to make a very sophisticated object detection. And of course, the human impression is, let me say, is a key factor while performing image analysis. But if we are going to use artificial intelligence, is the computer that is performing this kind of task. And the main challenges in this area is that there are no two areas that are really the same, exactly the same. So the parameters are constantly updated, and the machine learning is trying to give predictive results as more data are analyzed. So it's able, this kind of algorithms of artificial and intelligence algorithms are able to learn, and then by themselves or trained by the operator, and then apply all this kind of intelligence through a huge amount of images. How to put the intelligence in artificial intelligence? Making a lot of training, okay? So training data makes the difference. So you need to train this kind of algorithm, and you need to have enough data for training this kind of algorithms. And even the attributes of training data, so the features that can be extracted from the imagery, can be used to train the system, okay, to help the system in order to discover new patterns, to discover new objects. And the attributes are the properties of the objects that you are trying to classify, like the size, the shape, the color, the texture. And then you can choose which attribute you can use to separate the different classes. And of course, the quality and the quantity of training data is directly related to the accuracy of your machine learning system. This is a key point. So as much as training data and even quality, very accurate training data you are collecting, much more better results you're going to have out of the process. And of course, be aware of pre-trained models, cats and dogs. So let's have a look on how you can apply machine learning to this geospatial industry. You can apply in different domains, like for land cover classification, forest fire prediction, crop disease detection, rooftop extraction, or even change detection, and at the end as target detection. So these are some of the domains that can be covered into the geospatial industry, but of course you can even think to much other, okay? But in these domains, these kind of algorithms and this kind of technology is already proven and is already giving very good results. But if we move from machine learning that has a very, let me say, high-level interaction between the operators and the machine, we can move to deep learning. And deep learning is a type of machine learning, but differs in the way how the system is trained and how the system is performing a classification. Deep learning is using a convolution neural network to train itself during the classification. And deep learning is removing all the manual identification of features in data, and instead is discovering the data, the designated patterns, let me say, that in the training data by itself, okay? When you build a deep learning model, you will pass from the image chips into the algorithms, and then you will do all, and then this algorithm will do all the work for you. But how, as Hexagon Geospatial, we can put in action artificial intelligence? Through our spatial modeler engine that is a specific engine that has been, let me say, built inside Airbus Imagine in order to automate very sophisticated workflows. And one of these workflows, of course, can even include artificial intelligence as machine learning or deep learning algorithms. Now, let's have a look on Airbus Imagine and what is Airbus Imagine itself. So Airbus Imagine is a software that is, let me say, turning pixel and points into actionable information quickly to improve the speed and the confidence in decision making. Is an operational software. We are not just speaking about the toolkit, but it's a proven operational software that is being used for many decades and in different kind of domains for remote sensing and photogrammetric analysis. Basically, Airbus Imagine is able to connect to a comprehensive support for imagery, radar, and vector data. So Airbus Imagine has the ability to connect directly to the sensor models, okay, to the original sensor models without making transformation, and to dynamically ingest this information into the viewer in order to have a further analysis. Of course, this is for electro-optic imagery, but even for other SAR images that are quite used in different domains. And of course, we can even add vector support, so like shapefiles or other databases, in order to have a full picture of the landscape and of the data available. And of course, we are even supporting point clouds as sensors, so not just electro-optic, not just, let me say, the remote sensing sensor, but even point cloud are fully supported and ingested. But once we connect to the data, we can then process the data inside the same environment inside Airbus Imagine, and we do have hundreds of image analysis and geospatial processing operators already available for the end users, okay? So just to connect all these kind of operators, and this can be done using a very intuitive user interface in order to build this process, to test the process, and then to deploy this process. And we can go from auto rectification to auto mosaicing to compression, and but through a very powerful automation and an extensive set of export formats. So we can connect, process, and export to other different formats as the customer wish. And at the end, of course, Airbus Imagine is giving us additional capabilities like for understanding what's happening through the images, okay, like change detection workflows, like build and analyzing terrain surface modeling, making object recognition through deep learning and other machine intelligence algorithms. And of course, this is really proven and already used by more than 10,000 of data analysts daily in the defense of observation, education, insurance, transportation, disaster response, and crop monitoring domains. Okay, so all these domains are already using this kind of technology in order to streamline their workflows and in order to get actionable information from the data. So as you can see, these are some screenshots showing you Airbus Imagine on the top left using the spatial modeler engine, another and Airbus Imagine with point cloud, SAR images, photogrammetric data. And of course, we can ingest all this kind of sensor together, even together, for extracting the information. And then we can deploy, okay, these, let me say, models from a standard, let me say, process on a desktop machine up to a service that can be run even on the cloud. So as you can see in this case, we are gathering all this kind of data, and then we are extracting information through this kind of workflow that is very simple to manage. If we look to a spatial modeler overview, that is our engine for building this kind of workflow. It is, it's like a box of tools, like a Lego, in which you can be a beginner at the beginner level or to a professional. You can build up to professional applications. So up to, like on this example, making a mosaic process, and everything will be done as a batch process, so without the interaction, the user, let me say, interaction, and it will goes directly through, let me say, the result of mosaicing, let me say, a set of images. So let's imagine, basically, the spatial modeler is embedded into Atlas Imagine. As I said, is an authoring environment as a graphical user interface that is helping you on finding this kind of, let me say, operators, to drag and drop operators, and to build these very sophisticated workflows. And you can pick operators from raster, vector, point cloud, and you can even have real-time feedback and previews. So you don't need to pre-process the data and then go to analyze the results, but you can get immediately the feedback from the engine as a preview, and then once you are satisfied, you can generate new information out of them. But you can even extend the spatial models in different ways using a Python scripting. So we do have the ability to call Python scripts and from existing models. So if you have already an algorithm that is deployed as a Python script, we can even ingest that one into the process chain, and we can, let me say, manage this process chain, or using a spatial models operators embedded into Python scripts as well, or we can even add the command line operators or spatial modeler SDK. Let's have a look now on how we can use spatial modeling using, let me say, a dynamic image processing. In this case, what you can see is a multispectral image and a panchromatic high-resolution image showing in the same let me say, geographic space. But what we want to do is to fuse this kind of information all together using a spatial modeler. So it's very, very simple. We just need to drag and drop the images into the spatial modeler graphic user interface, and then we can easily drag, let me say, operators, and we can connect this operator easily once they are available into the user interface. And as you can see, we are building, let me say, a workflow, okay, directly without making any kind of coding, any kind of programming, but simply connecting operators all together. And you can connect many operators as you wish, and then we have just a preview operator. The preview operator is displaying in real time the results of this high resolution image. We can even change the parameters, as you can see here, changing the kernel parameters from 727 to 3 pass in order to get the better results, better resolution results. And this is done in real time dynamically for you using this spatial modeling engine. So let's have now a look on how we can put artificial intelligence in action using Atlas Imagine and using the deep learning operators that we have available inside Atlas Imagine itself. So artificial intelligence is fully embedded into Atlas Imagine through Spatial Modeler, and what we are using is TensorFlow as a main, let me say, engine in order to encapsulate this kind of technology into spatial modeler. But what we have done is that we have extended this capability of TensorFlow, especially for the geospatial context, especially for the geospatial domain, and even the ability to use this kind of very sophisticated deep learning and machine learning algorithms into a very, let me say, smart approach using a spatial modeler. So if we look to machine learning classifying in spatial modeler, we do have different capabilities for feature extraction, object and pixel classification, and even learning change detection. And this is covering different domains, so we can use this kind of agnostic operators in two different domains. So they are not a kind of black box, but you can use them, you can combine them all together in order to enhance your analysis and your processing workflows. So let's have a look now on the steps to classifying images using machine learning algorithms. So you prepare training data, you select the machine learning algorithm you want to use, you train the machine learning algorithm, and you validate the training data. So this is the first step that you need to start in order to, let me say, begin this kind of workflow in order to train the system on finding specific patterns into your own images. But then, of course, out of the validation of the training, you have to select the image you want to classify. It could be one single image or multiple images at the same time. You can select the trained machine learning algorithms, execute the machine learning algorithm, and at the end, you have the image classified result. So this is a process that is fully embedded into Airbus Imagine, and you can use it directly from a user interface. Let's have a look now on some use cases in different domains so we can prove how easily is to use this kind of technology inside Airbus Imagine without programming and without coding and for embedding these kind of algorithms. So the first use case is an object detection using deep learning for mapping oil palm trees locations into RGB photos. So the first step, of course, is to create training footprints and chips using the machine learning layout tools. Airbus Imaging is giving us a specific machine learning layout in order to facilitate the operators on, let me say, collecting training data. Okay, so you don't need to struggle with different workflows or different other, let me say, interfaces, but directly from the interface of Airbus Imagine, you have a specific layout that is specifically built in order to collect this kind of training data. When you want to train this data, you need to specify, which is, of course, what kind of objects you want to collect. So if you want to collect the image chips, object footprints only, or both chips and footprints as well, and you need to specify a specific folder where to store this kind of information in order to run then the training process. So everything will be registered into your computer or into your server or network, whatever you want. You just need to be able to reach this kind of folders. And then you can start to build your classification themes and class. So in this case, you want to classify an oil palm. And so just that, but you could have even, let me say, multiple different items, objects you want to classify. And in this case, you are now trying to locate some training data, like in this case, very, very simple. So we are locating and, let me say, using the footprints. In this case, we are using a variable footprint because, of course, all the trees they do have different shapes and let me say different angles. So we need to have a variable footprint available. We can save the footprint at the end of the process, and once the footprint is saved, then we will move to the next step, that is to train the system on using this footprint for the process. And this is a very streamlined process. So we just need to move this to this interface in order to train the system through the machine intellect output. So we are going to initialize the object detection and then to write it into the machine intellect output that is basically the engine that it will be used then in order to discover all the palm trees into our own image. So this is still inside the spatial modeler, as you can see here. So it's still the same interface, very easy to use and nothing to be changed, no programming code, but everything it will be done for you directly. So once we are able to run this process, we will have, let me say, the capability to extract directly from this, let me say, all the footprints using, let me say, the detect objects deep learning algorithm that is using as an input the machine intellect output that we have generated before. And as an output, we will receive vector data that are identifying all the footprints into the image itself. So there will be, let me say, no interaction at this point between the operator and what has been generated. And what is going to be generated are all the footprints that are identifying the palm trees around the image, around our own image. There could be some false positive, but let me say, probably the 99%, close to 100% of all the palm trees in this case have been identified. But on the other side, we have another kind of classification using deep learning that is a tile-based image classification. So we are able to classify images, dividing them into logical grids. So basically, we are creating a logical grid that is dividing, let me say, the image. And inside this image that is being logically divided, so not physically divided, we can still apply the same concept of training the model, okay? We are going to train a model and like this example, and using a different directory, different model at the same time. And once we are training the model, then we are going to apply the model grid by grid. So every single grid is going to use the same model, okay, in order to streamline, let me say, the process. Okay, in this case, the operator will be able even to review, let me say, the percentage of what has been discovered and during the process, and he can even, let me say, validate what has been discovered during this time. So we are going to run this process. The process is fully batch process that is going to run at this point, and the result will be based on the classification probability rank. So we will have a ranking with the probability value that is discovered. So as you can see, we have a value that is showing me based by every single tile of the grid what is the probability that this is a road, or that this is a building, or a swimming pool, or whatever. And we can move around this grid one by one, and we can validate. So we can mark them if they are correct, if they are wrong, and we can use even this mark, the next step, the next, let me say, in the next workflow, in order to improve the quality of what can be, let me say, found inside the image automatically. So this is a nice way in order to, let me say, balance the full automation with the full control of the operators. So in this way, you have a full control, and you can even export this kind of, let me see, report as an Excel file with the predicted probability that has been found out by the software. So you have not just a look into the final results, but you even have some KPIs available for you. If we move to another domain, in this case, we are using object detection with deep learning for vessel detection for the maritime domain, okay? Still, we are using the same, let me say, layout, predefined layout with some additional tools that you can build inside the Airbus Imagine interface. In fact, the Airbus Imagine interface gives you the ability even to customize the layout interface just for using your specific tools, okay, in your toolbar without, let me say, losing productivity. In this case, we are classifying 3 different classes: ships, water, and land, in order, let me say, to discriminate between ships and all the other classes that we could find inside the sea, since these has a different, let me say, response, radiometric response into the image. So now we are getting some footprints and chips of all these ships in this sample imagery that is representing our training data. And then we are going to move to water. So we are now training the system in order to collect and to identify water bodies and around an image. And then, of course, classifying the, let me say, the land shapes and of this specific area. So at that point, once we are going to classify another image, another similar image, all these items will be classified correctly for us without having, let me say, user interfacing from the operator. So in this case, we are still saving the same, let me say, model and data into the same, into another folder. So we can still maintain the machine intellect into a specific, let me say, folder. We run the process, and at this time, we are still running into this batch process. After this result, then we can move on making, let me say, object detection classification process. So using the image to be classified, using the machine intellect that we have just been generated, we can even add some additional parameters like the die size, and then we can just, we need just to input a result that in this case will be directly a ship file. Okay, we're going to run this process again, and the result out of it will be the classification of the ships done based on the footprints of the ships. And in this case, we are even filtering the result of the shape file using the filter, because we just want to see as a result the ships over a specific image. Okay, so we run this process. Now we filtered the data directly, and now we can open the new image that is being used as, let me say, as an input. As you can see, it's a different image from the previous one, different vessels as well, okay, with a different content. And here you can see the classified footprints that has been identified. Okay, so as you can see, just let me say, the big vessels that we want to identify has been identified. The small ones that we didn't select it before
are not identified by the system. So we have still a very good response from the system itself. And then we can still make image classification. So specifically for land use and based on machine learning algorithms, in this case, in this kind of scenario, we are using information derived from a photogrammetric photo and the location of the training polygons to train the random forest algorithms. So we are collecting points on a specific image in order to classify the land use like forest, green area, urban area, roads, or whatever. And once we collect the vector points, so this is the merge of not just of the footprints, but we are really making a classification of the image itself. And in this case, we are still using the same spatial modeling engine by using a different kind of algorithm. So we are using a random forest algorithm that is going to classify, let me say, the input image as a trained image, and then we can select the attributes as an input of the vector data that we are going to collect. So out of it, of course, we can select which kind of attributes to be used as an input of the vector data that are going to be used for, let me say, building the machine intellect output. So in this case, we can use a different kind of queries in order to combine and different outputs to combine all this kind of information together. And once we are selecting these attributes, then we can, let me say, simply run the process here that you can see for initializing the random forest and building the intellect machine output. So the new name of it, and then we can simply run the process. Once the process is out and is finished, then we can still use it as an input of, let me say, the classification model using machine learning. So you have the machine intellect output that we have trained before using the vector data, and now we are going to classify using the machine learning algorithm, okay? And using a different image, we still run the process, okay? So at the end, we get the result, and what we are going to see is a classified image, okay? But we are going to now to build a new viewer inside Atlas Imagine and to visualize the classified thematic image that you can see. So the image is fully classified, okay, with different thematic classes for water or corn or background or forest or whatever. So here we do have a classification fully automated, done using a machine learning algorithm within Atlas Imagine. Let's move now to the conclusion of this webinar. And so I just want to give you some artificial intelligence insights. So what we are providing using Atlas Imagine for artificial intelligence is a pre-configured solution. So we are not just delivering a toolkit, and this is giving you the ability to quickly assess, manage, conduct analysis, authoring, and fuse information in one single package. And you can implement your result-oriented and use case-specific solutions. So since we are using, let me say, the state-of-the-art technology for machine learning, but we are using it as an agnostic, let me say, input for your own data, then you can make and you can design tailor-made processes and solutions using this flexible platform. You can exploit the full potential of imageries, because imageries, yes, they are, if you have a huge amount of imagery and you need to analyze them, it's very important to be able to extract, let me say, information and to deliver actionable information out of this huge amount of data. So not just data, but moving from data to information. And of course, we are improving the stakeholders' knowledge and decision makings because we are delivering information directly to support different domain requests. So we can support different domains, different areas of expertise, and even different end users using this kind of COTS platform. So I want to thank you for this participation to the webinar, and I hope that you enjoyed the webinar for us. And here we do have some, let me say, connection to our website, trainings, webcasts, so you can even contribute to our own community. And you just need to go to community.hexagongeospatial.com, and then you can communicate with us directly, but even within the user community. And I hope you enjoyed this webinar, and I say you goodbye.
Thank you, Simone. So I think we have just a few questions that we'd like to cover before we let you go. I think we've got a few minutes. So question number one for you, how much is customizable of your workflow using the spatial modeler?
So as you have seen, Spatial Modeler gives you the ability to drag and drop different operators coming within Atlas Imagine, but we have the ability to even integrate external tools using Python scripting, using our own SDK, or using command lines operators.
Oh, very nice. Next question, can your deep learning technology be used by non-AI experts, or do you really need to be a developer to manage it?
As you have seen from this presentation, everything is driven by our own user interface. So this means that you are guided through this process. So you don't need to be an artificial intelligence expert, but you need to have your own expertise in your own domain, of course. But if you want to extend the capabilities of a specific model, this can even be done by a developer. So if you are a developer, you can even extend it. So you have a full flexibility in this case for using our own interface and capabilities, and even extending our own capabilities.
Oh, that's wonderful. One more question. Are you able to run this kind of ML or DL on different images, or is it sensor specific, even of radar images?
So our, let me say, machine learning and deep learning workflows and algorithms can be used on any kind of sensor that Atlas Imagine can ingest, okay? So we are not sensor specific, and we do not have limitation on the number of sensor on which we can use this kind of technology. And of course, even on SAR images, we can use a deep learning algorithm for making classification, for example, for extracting roads network directly from, let me say, a SAR image, or for making other kind of, let me say, workflows for enhancing a radar image, like the speckling the radar image.
Well, wonderful. Thank you so much. We really appreciate you sharing your expertise, and thanks also to Catherine for her help with logistics. And we just hope everyone has a great day and tells a friend about Hexagon Geospatial and Erdos Imagine and Directions Magazine. Thanks, Simone.
Okay.
Have a great day.